This is an automated approach to modeling Jupiter's synchrotron radiation from radio telescope observations. I'm Connor Espenshade.
I am Jay Sarva.
And I'm Peyton Robertson.
We are all high schoolers from Stanford Online High School. The image at right shows Jupiter's magnetic field. A process known as synchrotron radiation occurs when a magnet bends the path of a charged particle, causing it to emit light that we can observe. The image shows where the magnetic field is stronger, and at these two poles we would expect the synchrotron radiation, and we find the synchrotron radiation is stronger here as well. The impact of this is controlling another uncontrolled variable for Jupiter satellites, one example of which is Juno, which observes water concentrations and atmosphere concentrations on the planet. Taking synchrotron radiation out would be a better way to understand more accurate data.
So in terms of data processing, there were three main sections to our process. So the noise removal, baseline subtraction, and Gaussian curve fit. So first we need to remove the noise from the data. So we use the 10 most adjacent points for each data point, we compared it to the 10 most adjacent points, 5 before and 5 after. And we used a different threshold to determine whether it needed to be removed or not. So of course, on the base, the threshold was lower than on the peak. Then on baseline subtraction, the baseline of the noise reduced curve was that lay outside the peak was set to a third-degree polynomial, which was sufficient enough for this particular data set. We then subtracted this baseline from the noise filtered data, which placed almost every measurement was not a part of the peak near 0. So then we wanted to fit that baseline fit reduced curve to a Gaussian curve. We used a Gaussian fit because it was a reasonable approximation for an Airy function, which is what we expected for this data. And then in terms of determining which fits were good and which were not so optimal, we had to check whether the half power width was constant between scans, just because it's a general feature of every particular telescope. So as you can see on the right, this is just a particular example of one of our Gaussian fits. These are some of the bad fits that we ended up throwing out in our analysis. So of course, these did not produce very nice Gaussian fits because of their non-standard half-power width. They're not necessarily bad fits, they just are not optimal for our data set and they need further investigation.
Yeah, so then we computed the flux basically by looking at each of the Gaussian fits and taking that highest peak value, that's the intensity of our source, and then we ran this for both Jupiter as well as a calibrator quasar. Because the intensity doesn't determine the flux, only the ratio between them can be expected to be constant on a particular day, since that's going to be dependent on local weather conditions. So we computed the intensity for Jupiter and the calibrator quasars. We used the known flux of the calibrator quasar that we found in the literature in order to compute the actual flux of Jupiter. Then we had to scale this for the distance between Earth and Jupiter because of the inverse square law. So these fluxes could be objectively used by the Juno probe. Then we wanted to compare this flux to something in order to use it effectively, because it's going to vary throughout Jupiter. So we queried the ephemerids database through JPL Horizons in order to find the CML at the time of each scan, the line of longitude that was currently facing Earth, in accordance with the System 3, which is the longitude system used for atmospheric rotation on Jupiter. Then we constructed a model of CML versus flux for each calibrator quasar. Obviously, the curve for the calibrator quasar 3C353 was significantly smoother, so we ended up constructing a model based off of this quasar. The data from the other one still is worthy of further investigation.
We developed two models, one a seventh order polynomial and the other a piecewise trigonometric. We found that by using the residual sum of squares that the 7th degree polynomial was more accurate, but we believe that the trigonometric piecewise made more intuitive sense, so we developed both. For future work, a larger data set would be very helpful in determining how Jupiter works over a longer span of dates with a greater variance in distance and different calibrator quasars. There are also other factors such as volcanic activity on Io, and we did calculate, we did do an initial investigation comparing the Jupiter central meridian longitude to the Io longitude over synchrotron flux, but as you can see in the image at right, it's inconclusive now. But sunspots and other solar events could be other magnetosphere disruptors and hence change the synchrotron radiation.
So in conclusion, this research has contributed directly to telescope data automation and the CML versus flux model. By investigating it, synchrotron radiation is getting closer and closer to becoming a controlled variable, and overall, it produces a greater understanding of Jupiter through radio astronomy.
Thank you so much.